Hi, everyone. This presentation was presented at the One Health and Development Symposium at the University of Guelph on May 9th, 2022. So I'll give the presentation as if I gave it at the symposium. So today I will be presenting work related to my thesis work and also on behalf of the global burden of animal diseases informatics. And the title of the talk today is called Overcoming Inconsistencies in Data Categorizations to Calculate Disease Burden Estimates. And the focus of this talk today is going to be on data. So we all learned in the symposium keynotes today about the One Health concept, but I just wanted to highlight that our understanding of One Health problems is rooted in data. As scientists, we want data to back our decisions and as a basis to further our knowledge of One Health. Calculating the global burden of disease on humans, animals, and crops is a way that we leverage data in One Health. The Global Burden of Disease, or GBD study, attempts to quantify human disease. Two researchers in the 90s started with one question: what are people dying from? By sharing data, collaborating, and concentrating efforts to solve a problem, the study has evolved into a global effort of over 3,000 collaborators. The study, which is coordinated by the Institute for Health Metrics and Evaluation at the University of Washington, is published annually in The Lancet and calculates the burden of 333 diseases and injuries and 84 risk factors in 195 countries and territories by age and sex from 1990 to now. The learnings from a meeting between the World Bank and GBD in 2015 illustrate how global estimates of disease burden can improve health impacts globally. Through the estimates from GBD, important health trends can be identified, such as those I have identified here. These findings illustrate how data can drive our understanding of disease, can be used to track our disease interventions, and how policymakers and public health officials can use data to understand and assess the drivers of disease in different demographics. The success of GBD has made other global burdens emerge, such as the global burden of foodborne disease, the global burden of crop loss, and the global burden of animal diseases, which all use data and collaboration to calculate these burdens. Specifically, they reuse pre-existing data, and that data is classified in a specific way, whether that be classifications of disease, species, or geographic regions, so that we can understand trends over time and space and by different disease. The global burden of animal diseases, or GBADS, has the goal of estimating the economic and health burden of disease on animals over time and by region through a knowledge engine. It is separated into 8 thematic groups, one of which is the informatics theme. We are aiming to combine data from different sources and make it accessible through a data portal. The data portal aims to make data fair, or findable, accessible, interoperable, and reusable to modelers and other GBAD stakeholders. We have started with calculating livestock biomass, which is a critical component of the calculation of animal disease burden estimates. Livestock biomass takes global livestock species population numbers and weights as inputs. In addition, GBADS wants to estimate biomass by age and sex of animal over time and across different countries and production systems. The estimation of biomass will not only be important within the GBADS analytical structure, but will have broader One Health implications as well. For instance, biomass is used in the estimation of greenhouse gas emissions as an input for antimicrobial resistance estimates, to estimate the burden of animal disease, and to understand food security and protein availability for the human population. So to calculate livestock biomass, we use national livestock population data by species and over time. And these data can come from a variety of different data sources, such as the World Organization for Animal Health, or OIE, ICAR, Central Statistics Offices, and the Food and Agriculture Organization of the United Nations Statistical Database, or FAOSTAT. However, with each new data source typically comes a new set of categorizations leading to inconsistencies in the categorization of livestock data across sources and over time. The meaning of different categories of data are defined by the concept of semantic interoperability. Semantics is a part of linguistics that is concerned with meaning. This means that a data user or system has to interpret the true meaning of the information. Bringing this to semantic interoperability, which is defined as unambiguous access and interpretation of data by different stakeholders. In other words, we should be able to know what the categories in data actually mean. And to be interoperable also means to be fair. The fair sharing principles mention interoperability as one of the key pieces of facilitating the reuse of data, of understanding how to describe the data to find it, and for improving the accessibility of data. FAIR describes the principles needed to leverage pre-existing data, such as the data needed for One Health efforts. And ultimately, when data are not fair, we can improve interoperability in attempts to facilitate the other principles represented by FAIR. To illustrate three core problems in using the data required for livestock biomass, I will show the Irish cattle population case study. The three core problems related to semantic interoperability are: livestock species are categorized in different ways between and within data sources and over time. Livestock species categories are poorly defined by metadata or data about the data. And the meaning of categories is ambiguous and difficult to interpret. So onto our case study for Ireland. We have identified 4 sources of data for cattle in Ireland: Biostat, the OIE, ICAR, or the International Committee for Animal Recording, and the Ireland Central Statistics Office. The FAO and ICAR have one category for reporting each: cattle and dairy cattle. The OIE and CSO provide more granular categories for cattle, where the OIE breaks them down by age and by utility, so like dairy versus beef cattle, and the CSO breaks cattle down even more granularly. But upon further investigation and inspection, and through reading the OIE annual reporting guidelines, we see that the cattle category from 2015 onwards does not actually always suggest that the cattle are total. They write, enter the total number of cattle and the number of establishments. If data has been entered for at least one subcategory, please indicate the number of remaining cattle that do not belong to these subcategories. This means that cattle is the total number of cattle if the country reporting did not enter populations for any of the subcategories. Otherwise, it is the number of remaining cattle after the populations in the subcategories have been entered. So with four data sources reporting population numbers for one species for one country, there are 21 potential categories. And in addition to humans needing to understand these categories, so do machines. This begs the questions: what do the categories mean? How are they interpreted? And how do they compare? Or are the sources semantically interoperable? An analysis of the total cattle population in Ireland by the sources that report total cattle indicate firstly that the OIE cattle category must be total cattle and not all subcategories plus the cattle category, as identified by the blue bar on the chart. In addition, we can see little agreeability between the populations reported by each data source, despite the fact that they're reporting the same thing. This presents ambiguity in the categories and suggests that the data sources do not interoperate and are difficult to interpret. Now, comparisons of the data cattle categories in CSO, ICAR, and OIE show that while all sources report the same population numbers in 2017, they are not equal in 2018. And in 2019, the CSO and OIE report the same numbers, but ICAR does not. Again, this shows that there are issues in data quality and in the semantics of the categories. Consider that our case study was only for one country and species. To create global estimates, we need to ensure that data is interoperable between and within countries too. However, learnings from our Irish case study highlight the importance of analyzing semantic interoperability to understand the inconsistencies in categorizations. This shows that this type of analysis is important when using data to find data, so to know what categories mean and to inform how to search and find data. For instance, if someone searches for dairy cattle, they should be able to get dairy cows too, and to understand the categories to inform technology system development. So we can design our software so that machines know what to give the user for a given request, regardless of their preferred vocabulary. And to reuse and combine data, which of course is really important for disease estimates and in One Health. So by understanding how categories are different and how they are interpreted by the various players in data, we can bridge data silos by making data from various silos accessible, and to understand how data can be combined and when categories mean the same thing, and to understand how data can be used. And finally, to present a shared interpretation of data. All parties involved in data flows must interpret data as it was intended to ensure that modeling outputs are unbiased and accurate, and that outputs are reproducible. And this can be done by explicitly stating where data is coming from to ensure that the outputs can be reproduced. For true One Health estimates, we need to bridge silos and develop a shared understanding of data between sectors and initiatives. This starts with analyzing data to understand what the vocabularies are in different disciplines and whether there's shared meaning between each. By analyzing semantic interoperability, we can overcome inconsistencies in data and develop a cross-sectoral understanding of data and begin to leverage the data used in all of the global burdens to create the idea of One Health data, which should be fair. Thank you.